How do you teach a computer to see a chessboard in images and videos? In part 1, we explored different classical computer vision approaches to solve this, eventually settling on a combination approach with things like edge detection, X-corners, convolutional neural networks, and optical flow to find and track chessboards in less than 1/10 of a second per image. In this video, we'll try to do this with the latest machine learning technologies instead. We'll go over the state of the art in ML object detection, dataset creation, and model design and training. It's an exciting journey, so stick around and let's find out if it's time to bow down to our machine learning overlords. What's ML like these days? Let me just do a little Googling and, holy crap, image classification and object detection have really taken off. It looks like around 2015, after ResNet took off for image classification, these residual networks opened up the field of object detection, divided into two categories, two-stage and one-stage, or one-shot, object detectors. Since 2015, flavors of RCNN dominate the two-stage detection process, basically image classification on proposed bounding boxes to find objects. Then in 2016, YOLO and SSD grew the field of single-shot object detection, using anchor boxes instead of proposals to do it all in one. The goal is to find the 3D position and orientation of the chessboard in space, which we can do by finding its four corners, but most object detectors are designed to find the bounding box of objects, which isn't enough by itself. As one approach, we could try training a custom model to directly find the four corners. I'm not sure what the best architecture for this is yet. As another approach, maybe we could use the bounding box of the chessboard to crop the image, and then pass the cropped image to a previous CV algorithm. That makes the problem much smaller and easier for the CV-based approach. This could work too. There are more options than this, and I think they may all work with different pros and cons. For now, let's focus on two, building a custom all-in-one model and a fine-tuned YOLO plus CV system. Place your bets on which one wins. My intuition thinks the YOLO plus CV might be more robust, but it will be slower because of the extra steps. But I have a feeling there's a lot of work to be done to make the custom model actually work. Either way, we need a decent amount of data with labeled bounding boxes. How do we get that? We could use the images from the past, but I only have tens of images. And while I could get some meh initial results with that, at the end of the day, we need more variety in the images. We really need hundreds to thousands of images. So what if we could make our own synthetic images instead? I've been wanting to learn how to create synthetic images for training anyway, and seeing how well that transfers to real images. I saw NVIDIA recently released a tool suite called Omniverse, and Isaac Sim for robotic synthetic dataset generation, which is super cool. I went ahead and installed all of this and started trying to go through the tutorials, and while they do work, my consumer desktop and GPU makes this a pretty laggy and slow experience. I think the system is a bit more tailored towards small companies with more resources. I then looked into 3D modeling software, since I have used things like Autodesk and SolidWorks in the past, and I found Blender, which has a Python programmatic interface and has been used to render incredible feats of animation. This seems awesome. Let's learn how to use Blender and make a chessboard in it. There are some really nice tutorials out there which I followed. And with that, I make a very bare bones chessboard to start, since I just want to see if I can get the full training process working in the first place. Okay, this is a super cool tool to have. I've made a basic chessboard, and then with Blender Python, I can randomly position the camera and light around the board and take an image each time. And we can use the perspective transform to take the 3D points of the four corners of the chessboard and turn them into the 2D pixel coordinates in our image space as the ground truth labels. Let's make a couple thousand images to start. Hey, the images look pretty good. Yes, they're pretty simple, but we'll add some basic data augmentation. And let's start testing out our approaches with this before trying to improve the dataset. Future Sam here. I do get around to improving the synthetic dataset, which I'll put in a future video, so definitely subscribe if you're interested in seeing that. I started in Google Colab because it's really easy to get going. You can use other systems besides TensorFlow like PyTorch, but this is what works for me. Let's start with a simple and common CNN pyramid model architecture, modifying the output to be 8 floats corresponding to 4 XY coordinates of the chessboard corners. Excitingly, the model actually seems to converge, but it has a hard time getting the precise positions. I'm interested in seeing if we can apply transfer learning here, so I started looking into using pre-trained models like MobileNet v2, which is a common starting point for many problems involving fine-tuning for image classification. We replace the last layer with a few dense layers and then our 8 float output layer. We keep the base model layer frozen, and train just these final layers. Training takes quite a bit longer on CPU. Luckily, Google gives free access to a T4 GPU instance for short periods of time, so I switch over to that, and training is blazing fast now. Holy crap, it kinda works! This is super cool. The concepts of objects and things that MobileNet has learned transfers quite well here. However, I do notice it is having a hard time getting the points accurately. This makes sense, because our CNN architecture keeps shrinking at each layer, so by the time we get to the final layer, or the tip of the pyramid, we have very little spatial information left from the start, so it has to try to learn this concept of spatial location separately in the filters, which is a lot of work for this poor little model. I'm going to switch to the next approach now. Future Sam again. I have been making some exciting progress with more advanced architectures like UNets and residual networks with a heat map based approach. Stay tuned for that video. This problem of spatial location is a pretty common one in object detection. Region proposal networks approach this by proposing multiple bounding boxes all over the image and then trying to classify those areas. Unlike RCNN, SSDs break up the image into a grid and try to learn a confidence for every single grid cell and bounding box for objectness as well as center XY offsets and width height scale factors to fit the real data. Do note that because there's so many more cells without objects, most naive models will just learn to predict no object all of the time. Going through the research papers, there's a ton of work going into designing custom loss functions that keeps the model from just giving up, and I could go down this rabbit hole for weeks. So let's take a step back and see if we can fine-tune an existing model first before we build our own. Let's fine-tune a tiny YOLO V8 model, since it's one of the faster models out there and it's relatively recent. I think they're on V10 now in research. Good job y'all, keep it up. At this point I'm constantly using up my free credits on Google Colab, so I'll switch to running everything locally on my desktop gaming PC with an NVIDIA RTX 2080 GPU. I'll use TensorFlow Keras on a Jupyter IPython notebook running on a Docker container on my Windows machine. I've installed TensorFlow with GPU on Windows like 20 times now, and I get frustrated by different things every time. Using a Docker container is super easy to get going. It uses a GPU perfectly, and really I wish I'd done this years ago. First, we load our pre-trained YOLO V8 model using Keras, modified with a single class output layer, and then we start training. I'm using Chessboard so we can watch the loss drop over time. I also have it predict on some synthetic validation data every epoch. The green box is the true bounding box, and the yellow boxes are the model predictions. Over time, it seems to slowly learn the location of the chessboards. How cool is that? Now we get to the million-dollar question. Will this model trained on synthetic images transfer to real images? It actually gets some! That's really exciting, and shows the model is learning the visual concept of a chessboard to some degree. But it isn't getting most of them. If we think about it a bit, this makes sense, because if we look between the real and synthetic images, the synthetic ones are quite obviously different, with their blank background, not to mention being only black and white, and without shadows or pieces or anything else. Let's add some backgrounds by using real images I've taken in the past, like of my room and conference rooms and stuff like that. We can randomly crop sections and paste the synthetic chessboard image on top of that. Since we exported from Blender with alpha transparency, this is a simple process. Let's also add some random pieces to the board. As a simple first approximation, we'll just use black and white cylinders as chess pieces, and randomly place them on the board. I render with the Cycles engine that uses my GPU to render with ray tracing, which gives us more realistic lighting and shadows. There's a lot of opportunities for improvement here. Instead of cylinders, we could be modeling the pieces more accurately. And instead of random tiles, we could download a bunch of real chess games and use the Fen notation from them to get real piece layouts to use here. I will get to that in a future video, so don't forget to subscribe if you're interested in seeing that, but we don't want to get sidetracked just yet. I am loving this Blender scripting system. It's very powerful, if only mildly intuitive, and after a few seconds we have our random images. Yeah, I'm pretty happy with that as a first pass. The shadows and coloring feel a bit closer to reality. Let's run this for an hour or two to make a couple thousand images. We'll split the synthetic images into the training set and the validation set, and the real images will be the test dataset at the end. The model only gets to learn from the training set, and we make sure it's not memorizing everything by testing it with the validation dataset. We can see it gets better and better at predicting images on the validation dataset with each epoch. So cool! Finally, we test the finished model on some unseen real photos, and it gets most of them! Not only does this show the ingenuity of the SSD architecture, but it also runs pretty fast, around 23 milliseconds per image. We can take the bounding box and pass the cropped image to the CV algorithm from part 1, and use that to precisely locate the chessboard in the image. Since the cropped image has more chessboard and less background, it becomes a simpler and easier problem for the computer vision algorithm. Look at that! It finds the boards in the bounding box faster than before. This is so cool! The entire system and model was trained with no real images, only synthetic ones. I'm really impressed with how well the synthetic data approach works for this problem. I wish I could have shown this to myself a decade ago. Now YOLO takes around 23 milliseconds, and the bounding box CV approach takes another 20 milliseconds. This is a bit more consistent, and it is finding chessboards in some images where it couldn't before, especially those where the board was small in the image, or there was a noisy textured wallpaper or something in the background. But the old CV approach did a pretty good job of zooming in on the chessboard already, and it still struggles on certain chessboards even with cropping, so the bounding box isn't helping as much as I hoped. This isn't a complete victory yet, but we are finding chessboards in images with YOLO, which is a great start. It's pretty exciting to think about directions to go from here. From modifying the inputs or outputs of YOLO, tuning the CV algorithm to fit, or improving the custom model architecture, and there are research papers out there like CenterNet that go in this direction. We should also improve the synthetic data generation to make even more lifelike images. Instead of cylinders, make them look more like pieces, and instead of random positions we could use random piece positions from real games. We could add fake hands and drinks in the way, more lights, multiple chessboards per image. A crazy idea, what if we ran the synthetic image through generative AI to make it look even more realistic? This rabbit hole could go down pretty far. We could go towards image segmentation, identifying pieces and boards on the image. I built UNet architecture style models that do this sort of thing for other problems in the past. What a fun problem this is, and if you made it this far, thanks for sticking with it. The next video I'll probably focus on building a better synthetic dataset with Blender, and perhaps try RCNNs or try YOLO again. You only live twice? YOLT? We'll also explore more custom architectures like UNets. So, which one do you think has more promise? Is classic computer vision dead to you? Let me know in the comments. I had a lot of fun making this video. If you enjoy this kind of content, please leave a like and subscribe to keep up with the future videos. Thanks for watching and see you in the next video. Cheers!